Welcome back. In this video, we're going to look at examples of using the direct comparison test to determine the convergence of series. Let's get to it. All right, so here's our first example. We want to use the direct comparison test to determine if the series converges or diverges. And so our first series is this series right here. We have the sum from n equals 1 to infinity of 1 divided by 3n squared plus 2. All right, now in this case, we were told to use the direct comparison test right away, but if you were just given a series and told to determine its convergence, the first thing that you would want to do is use the divergence test to see if your series diverges, because all you have to do is take a limit of your series as n approaches infinity and see if it's not equal to 0. But if it is equal to 0, like all of the series in this video will be, then of course the divergence test is inconclusive, and you would need to use another test. Okay? And so for this series, we know we want to use the direct comparison test. And so how are we going to do that? What series can we compare this series to in order to determine if it converges or diverges? Well, what we want to do is look for features of our series that look similar to features of series we do know how to determine the convergence of. And so that includes a geometric series, a p-series, or even a series that maybe we can use the integral test for. But in most cases, you're either going to be looking at a geometric series or a p-series. All right, and so what type of series is this series similar to that we could make a comparison between? Well, we have 1 divided by 3n squared plus 2. If we ignore that plus 2, we have 3n squared. N squared in the denominator is in the form of a p-series, right? The form of a p-series is 1 divided by n raised to some power. It doesn't matter if it's being multiplied by a constant, the general form is 1 divided by n raised to a power. And so what we can do is compare this series to the p-series, where we have the sum from n equals 1 to infinity of 1 divided by 3n squared. All right, and that would just be equal to 1/3 times the sum from n equals 1 to infinity of 1 divided by n squared, right? We could just pull that 1/3 to the front of the sum, and now you can see our p-series that we can determine the convergence of. And so in this case, we have 1 divided by n squared, and so the power of n is 2, which means that for our p-series, p is equal to 2. And we know for a p-series, when the value of p is greater than 1, like 2, that the series converges. And so in this case, 2 is greater than 1, and so our p-series converges. Okay, so we know that this series that we are comparing to our original series converges, but does that mean that our original series converges as well? Well, if you remember what the direct comparison test says, if we have two sequences, b sub n and a sub n, where b sub n is greater than or equal to a sub n, and both of those sequences are greater than 0, meaning that their terms are positive, then we can make the following comparisons. And remember that b sub n is the larger sequence because it's greater than or equal to a sub n, so all of its terms will be larger than a sub n. And so if the series for that sequence, b sub n, converges, then the series for the smaller sequence converges as well. But if the series for the smaller sequence diverges, then the series for the larger sequence diverges as well. And this only works in one direction. We can't say the opposite of each of these statements. We can't say that if a smaller series converges, then the larger series converges, and we can't say that if a larger series diverges, that a smaller series diverges. And I show why this is true visually in my lesson video if you haven't watched that. But for this video, we're just focusing on using the comparison test, not necessarily why it works. Okay, and so essentially what the comparison test allows us to do is if the series we are comparing our series to is larger and it converges, then our original series converges as well. But if it's smaller and it diverges, then our original series will diverge as well. So now if we go back to our example, we found that the series we are comparing our series to converges, and so we're hoping that this series will be greater than this series. All right, and so let's compare the two series. Let's compare 1 divided by 3n squared plus 2 to 1 divided by 3n squared, right? This is the nth term for our original series, and this is the nth term for our series that we are comparing to that series. All right, and so can we conclude that the series we are comparing to our original series is greater for all values of n? Well, if you look at these two expressions, the original series has a denominator of 3n squared plus 2, and the other series just has 3n squared. So the only difference between the denominators is this plus 2. And so this denominator will always be 2 greater than this denominator. And so when you have a larger denominator, that value will be smaller than the other value, right? 1/4 is less than 1/3 because 0.25 is less than 0.3 repeating, and 4 is a larger denominator than 3. All right, and so when the denominator is larger, the value will be smaller. And so for all values of n, this expression will be less than this expression. And so our original series will be smaller than our series we are comparing it to. And so the original series is the smaller series, and our comparison series is the larger series. And so since that larger series converges, we can conclude that our smaller series, or our original series, also converges. So we can say that since the larger series, the sum from n equals 1 to infinity of 1 divided by 3n squared converges, that the original series, or the smaller series, the sum from n equals 1 to infinity of 1 divided by 3n squared plus 2, must also converge. Okay, so that is the final solution to this example. We have determined that our original series converges because the series we compared it to converges and it is larger than that series. Okay, let's look at another example. All right, so next up we have this series. We have the sum from n equals 0 to infinity of 4 to the power of n divided by 9 to the power of n plus 3. And once again, we want to use the direct comparison test to determine if it converges or diverges. All right, and so what series that we know the convergence of can we compare this series to? Well, if we look at the features of this series, we have 4 raised to a power of n and 9 raised to a power of n. And so this looks very similar to a geometric series, where we have some value raised to a power of n. Right, so if we ignore this plus 3 right here, we can compare this series to the following geometric series. The sum from n equals 0 to infinity of 4 to the power of n divided by 9 to the power of n. And of course, that would be equal to the sum from n equals 0 to infinity of 4/9 to the power of n. Right, since the numerator and denominator are both raised to the power of n, we can just take that whole fraction to the power of n. And this is a geometric series whose convergence we can determine. We have a value raised to a power of n, and that value is known as the common ratio r, and so r is equal to 4/9. And when the absolute value of the common ratio is less than 1, then the geometric series converges. But if the absolute value of r is greater than 1, then the series diverges. But in this case, 4/9, the absolute value of that would just be 4/9, and that is less than 1, which means that this geometric series converges. Okay, and so since we have found a series to compare our original series to that converges, what we want to show now is that this series is greater than this series, that we have a larger series that converges compared to a smaller series that we want to show also converges. And so if we compare our two series, we have 4 to the power of n divided by 9 to the power of n plus 3, and 4 to the power of n divided by 9 to the power of n. The only difference between these two expressions is this plus 3 in the denominator. And so no matter what value of n we are looking at, this expression will always have a denominator that is 3 greater than this expression. And so since this denominator will always be larger than this denominator, this value will always be smaller than this value. And so we can say that 4 to the power of n divided by 9 to the power of n plus 3 is less than 4 to the power of n divided by 9 to the power of n. And that will be true for all values of n greater than or equal to 0. Okay, so no matter what value of n we use, the terms of this series that we are comparing to our original will be greater than the terms for that original series. And so we have found a series to compare to our original that is a larger series and it converges, and so we can conclude that our original series converges as well. And so what we can say from the direct comparison test is that since the larger series, the sum from n equals 0 to infinity of 4 to the power of n divided by 9 to the power of n converges, then our smaller series, the sum from n equals 0 to infinity of 4 to the power of n divided by 9 to the power of n plus 3 must also converge. All right, and so that is the final solution to this example. We found a series to compare to our original series that is bigger and converges, and so our original series must also converge. All right, so here's our next example. We have this series, the sum from n equals 1 to infinity of 1 divided by the square root of n cubed plus 1. And once again, we want to use the direct comparison test to determine if this series converges or diverges. And so what type of series could we compare this series to in order to determine its convergence? Well, if you look at its structure, we have 1 divided by the square root of n cubed plus 1. And so between a geometric series and a p-series, it seems like this series is the closest to a p-series. Right, we have 1 divided by n raised to a power underneath a square root, and that's fine. We can actually compare this series to the sum from n equals 1 to infinity of 1 divided by the square root of n cubed. We can just remove that plus 1, and now we have a series that is in the form of a p-series, right? This would be equal to the sum from n equals 1 to infinity of 1 divided by n cubed to the 1/2 power, right? The square root of a value is the same as taking that value to the 1/2 power. And when you have a value raised to a power, you can simplify by multiplying those exponents. And so 3 times 1/2 is 3/2. And so what we really have here is 1 divided by n to the 3/2 power. And so this is a p-series of 1 divided by n to the power of 3/2. And so p for the p-series is equal to 3/2. And now that value of p is greater than 1, which means that our p-series converges. All right, if it was less than 1, then our p-series would diverge instead. But now we have a p-series that we are comparing to our original series that converges, and so now what we want to show is that this series is greater or bigger than our original series. Because when a series is bigger and converges, we can conclude that the smaller series also converges. Okay, so if we compare our two series, we'll have 1 divided by the square root of n cubed plus 1 and 1 divided by the square root of n cubed. Now if we compare these two terms, the numerators are the same, but the denominators are different, and they only differ by this plus 1 underneath the square root. And so no matter what value of n we plug in, we're going to be cubing that value of n, but for this expression, we then add 1 to it before we take the square root. And so no matter what value of n we plug in, this denominator is going to be larger. We're adding 1 to that value of n cubed, and then taking the square root of it, which is always going to be larger than just the square root of n cubed. The square root of a larger number will be bigger than the square root of a smaller number. And so for all values of n, we can say that this expression will be less than this expression. The denominator is always bigger, and so that value will always be smaller. And that is true for all values of n greater than or equal to 1 for our two series. Okay, and so now we have shown that our series that we are comparing to our original series is bigger. The terms of that series will be larger than the terms of our original series. And so because we have shown that this series is bigger and it converges, then we can conclude that our original series, which is smaller, also converges. And so, since the larger series, the sum from n equals 1 to infinity of 1 divided by the square root of n cubed converges, then the smaller series, the sum from n equals 1 to infinity of 1 divided by the square root of n cubed plus 1 must also converge. All right, and so that is the final solution to this example. We found a series that converges that is always bigger than our original series, and so that series must also converge. Let's take a look at another example. All right, so next up we have this series, the sum from n equals 1 to infinity of 1 divided by 3n minus 1, and we want to use the direct comparison test to determine if it converges or diverges. All right, and so what series can we compare to this series that we know the convergence of? What type of series does this series closely resemble? Well, if we look at the form, we have 1 divided by 3n minus 1. And so if we remove that minus 1, we would just have 1 divided by 3n, which would be in the form of another p-series, right? So once again, we can compare our series to a p-series. So we'll have the sum from n equals 1 to infinity of 1 divided by 3n, and that would just be equal to 1/3 times the sum from n equals 1 to infinity of 1 divided by n, right? We can always pull out a constant multiple to the front of the series, and now you can see that we have this p-series. In fact, it's a special p-series known as the harmonic series because the power of n is equal to 1, right? We just have 1 divided by n to the power of 1. And so since p is equal to 1, this p-series diverges. The harmonic series is a divergent series. And so here we have a series that we are comparing to our original series that diverges. And so we don't want this series to be greater than our original series. We want it to be smaller, right? When the series that you are comparing to your series diverges, you want to show that that is a smaller series. And so if we compare the terms of our two series, we have 1 divided by 3n minus 1 and 1 divided by 3n. Which one of the terms is going to be greater for the values of n? Well, if you look at these two expressions, they both have the same numerator, but the denominators differ by just this -1. This denominator will always be 1 less than this denominator, which means that this denominator is always greater. And when the denominator is greater, the value of that expression will always be smaller. And so we would say that 1 divided by 3n minus 1 will be greater than 1 divided by 3n. That denominator will always be smaller, and so the value of this expression will always be greater. And that is going to be true for all values of n greater than or equal to 1. And so now what we have shown is that the series that we are comparing to our original series is smaller than our original series. The original series is the bigger series, and the series we are comparing is the smaller series. And since the smaller series diverges, then we can say that our bigger series, or the original series, also diverges. All right, and so we can say that since the smaller series, the sum from n equals 1 to infinity of 1 divided by 3n diverges, then the larger series, the sum from n equals 1 to infinity of 1 divided by 3n minus 1, must also diverge. Okay, and so that is our final solution to this example. Now, before we move on to our next example, just note that if we found that our comparison series was bigger than the original series, then we could not make this conclusion. It needed to be smaller since it diverged. If it diverged and it was bigger than our original series, then we would need to pick a different series to compare it to in order to make any conclusions. Okay, so when your comparison series is smaller, you can only make a conclusion about the original if it diverges. Okay, and so just keep that in mind going forward. All right, so here's our next example. We want to use a direct comparison test to determine if the series converges or diverges, and we have this series this time, the sum from n equals 1 to infinity of 1 divided by n factorial. All right, and so what type of series that we know the convergence of can we compare this series to, right? We have 1 divided by n factorial. That doesn't look like any type of series we know how to easily determine the convergence of, right? It doesn't look like a p-series because we don't have 1 divided by n raised to a power, And it doesn't look like a geometric series because we don't have some value raised to the power of n, and so we're kind of at a loss here. We don't exactly know what to compare this to, right? It doesn't have any similar features. Well, even though it doesn't have any features that we can recognize, we still can compare it to a p-series, right? We still have 1 divided by n factorial, so we do have a value of n in the denominator, and so maybe we can compare this to a p-series where we also have n in the denominator, but raise it to a power. All right, and so what we're going to do is compare this to a p-series. And so let's just start with the very basic p-series, the harmonic series, where we have the sum from n equals 1 to infinity of 1 divided by n. All right, so in this case, p is equal to 1, and the harmonic series diverges. And so what we want to show is that this series is smaller than this series. And then we can conclude that this will also be divergent. And so if we compare our two series, we have 1 divided by n factorial and 1 divided by n. And so if we look at the first couple terms, when n equals 1, we will have 1 divided by 1 factorial and 1 divided by 1. Those terms will just be equal because 1 factorial is 1, and 1 divided by 1 is 1. So we just have 1 is equal to 1 when n equals 1. And so let's look at n equals 2. When n equals 2, we have 1 divided by 2 factorial equal to 1 divided by 2. And 2 factorial is just equal to 1 times 2. And so we just have 1/2 is equal to 1/2. So once again, our terms are equal. And so let's move on to n equals 3. Now we have 1 divided by 3 factorial, and we're comparing that to 1 divided by 3. Now 3 factorial is equal to 3 times 2 times 1, and 3 times 2 is 6, times 1 is still 6, and so now we have a different denominator of 6, all right? And so 1/6 is smaller than 1/3, right? Now we have a term that is smaller than another term. Now if we look at the next term, we'll have n equals 4, and that will be 1 divided by 4 factorial, and that is going to be compared to 1/4. Now 4 factorial is 4 times 3 times 2 times 1, and that is equal to 24, so now we have 24 in the denominator, and 1/24 is way smaller than 1/4. All right, and so that is going to continue to happen for all future terms of both of these series. The term for 1 divided by n factorial will be smaller than the term for 1 divided by n after n equals 2, right? Starting with n equals 3, that is what's going to happen. But remember, we want our series that we're comparing to the original series to be smaller than the original series in order to conclude that this also diverges like this series does. But that's not the case, right? We have just shown that 1 divided by n is going to be greater than 1 divided by n factorial for values of n greater than or equal to 3. And so in the long term, this series, 1 divided by n, is going to be larger than 1 divided by n factorial, and so we can't say that this series will also diverge like this one. And so this was kind of a bust. We cannot conclude anything about this series by comparing it to 1 divided by n. And so let's back it up a little bit. We're going to have to compare to a different series in order to make any conclusions. And so all I'm going to do is just change this series a little bit. Instead of looking at 1 divided by n, let's look at 1 divided by n squared. Then maybe we will be able to make a conclusion about our original series based on this comparison series, right? And so this is still a p-series. We have 1 divided by n raised to a power, but this time p is equal to 2, and that is greater than 1, which means that our p-series converges. And so this is a different result than what we found earlier, right? 1 divided by n was a divergent series, but we couldn't conclude that this series also diverged, and so maybe what we need to do is look at a convergent series instead, and let's see if this series is larger than this series, because if a larger series converges, then the smaller series will also converge. All right, and so instead of comparing 1 divided by n factorial to 1 divided by n, we will compare it to 1 divided by n squared. And so let's look at the first couple terms. Let's see if 1 divided by n squared will be bigger than 1 divided by n factorial. So for n equals 1, we're going to have 1 divided by 1 factorial and 1 divided by 1 squared. both of those expressions are just equal to 1. So in this case, when n equals 1, we have that our terms are equal. They're both 1. But when n equals 2, we're going to have 1 divided by 2 factorial versus 1 divided by 2 squared. Now 2 factorial is 2, and 2 squared is 4, so we have 1/2 and 1/4. All right, and 1/4 is smaller than 1/2. All right, so we have 1/2 is greater than 1/4. Now if we look at n equals 3, we're going to have 1 divided by 3 factorial and 1 divided by 3 squared. And 3 factorial is 3 times 2 times 1, which is 6. So we will have 1/6. And 3 squared is 9. So we will have 1/9. All right. Now 1/9 is smaller than 1/6, right? 9 is a larger denominator than 6. And so 1/6 is greater than 1/9. And now let's look at n equals 4. We will have 1 divided by 4 factorial and 1 divided by 4 squared. Now things are going to flip on us. 4 factorial is 4 times 3 times 2 times 1, which is 24. So we have 24 in the denominator, and 4 squared is 16. And so we will have 1/16, and 1/24 is less than 1/16. That denominator is bigger than this denominator, so this value will be smaller. All right, so we started out with equal terms, and then 1 divided by n factorial was greater than 1 divided by n squared, but now it has flipped. And from this point forward, it's never going to flip again. The denominator of n factorial is going to increasingly get larger faster than n squared, right? And you can see this with n equals 5. We will have 1 divided by 5 factorial and 1 divided by 5 squared. 5 factorial is 120 because 5 times 4 times 3 times 2 times 1 is 120. And so we have 120 in that denominator. And then 5 squared is just 25. So we have 1/25. And 1 divided by 120 is less than 1/25. All right, so from n equals 4 forward, all of our terms for 1 divided by n factorial will be smaller, which means that 1 divided by n squared is greater than 1 divided by n factorial for n greater than or equal to 4. All right, so for all terms, for n greater than or equal to 4, this series will be greater than this series. It doesn't matter that the first couple terms don't follow that pattern. In the long term, this is a greater series, okay? And so since we found a series that is greater than the original and it converges, we can conclude that the original series also converges via the direct comparison test. All right, and so what we can say is that since the larger series, the sum from n equals 1 to infinity of 1 divided by n squared converges, then the smaller series, the sum from n equals 1 to infinity of 1 divided by n factorial, must also converge. All right, and so that is the final solution to this example. We have determined that this series converges because we compared it to a bigger series that converges itself. All right, let's look at another example. All right, next up we have this series, the sum from n equals 2 to infinity of the natural log of n divided by n. And we want to use a direct comparison test to determine if it converges or diverges. All right, and so what can we compare this series to in order to determine its convergence? Well, we want to look for any familiar features to series that we do know the convergence of, and so we have the natural log of n divided by n. And so between a p-series and a geometric series, I would say that this more closely resembles a p-series because we have a value divided by n raised to a power. In this case, it's just n to the first power, but that's still something that we could compare this series to. And so I'm going to start with that. Let's compare this to the series where we have the sum from n equals 2 to infinity of 1 divided by n. All right, we're just going to remove that natural log function because that is the part of this series that makes this series not a p-series. That's why we can't just test this series right away using the p-series test. It needs to have 1 or some other constant in the numerator, not a function like the natural log function, in order to use the p-series test. So instead, we're going to compare that to the p-series of 1 divided by n. All right, and so this is a p-series where n is raised to the first power, so p is equal to 1, and so that means that this series diverges, right? It is the harmonic series. It doesn't matter that it starts at n equals 2. Removing a couple terms from the beginning of a series, even if it's just one term, right? We're starting at n equals 2 instead of n equals 1. That's not going to affect the convergence or divergence of a series. It will affect a sum, but it doesn't affect whether it converges or diverges, and so we are allowed to conclude that this series diverges because the value of p for the p-series is equal to 1. All right, and so now what we want to show is that this series, which diverges, is smaller than our original series, right? In order for this series to also be divergent, that series we are comparing it to needs to be smaller. And so if we compare the terms of our series, we have the natural log of n divided by n and 1 divided by n. All right, and so between these two terms, the denominators are the same, but the numerators are not. And so we want to compare the numerators this time around. And so the natural log of n is going to change based on the value of n. And so if we start with n equals 2, which is where our series starts, let's see what the natural log of 2 is. The natural log of 2 is approximately equal to 0.69 and some more decimals. When n equals 3, the natural log of 3 is approximately equal to 1.09 and some more decimals. And then from that point on, if we were to look at n equals 4 and so on, the value of the natural log of that value of n is going to continue to be greater than 1, right? The natural log of 4 is approximately equal to 1.38 and some more decimals. As we plug in larger and larger values of n into the natural log function, it is going to output larger and larger values. And so after n equals 2, this numerator will be greater than 1, which means that this expression will be greater than this expression, because this numerator is always 1, and so if this is greater than 1 and the denominators are the same, then this value will be greater. All right, and so after n equals 2, meaning that we start with n equals 3, we would say that the natural log of n divided by n is greater than 1 divided by n. All right, and so that is true for n greater than or equal to 3. So for the long term, this series is smaller than our original series. And that is exactly what we wanted to show. Since this series that we are comparing to the original diverges, we wanted to show that this is smaller than the original so that we can conclude that the original also diverges. All right, so it doesn't matter that the first term would be smaller. In the long run, for all values of n greater than or equal to 3, this series is smaller. And so we can say that since the smaller series, the sum from n equals 2 to infinity of 1 divided by n diverges, then the larger series, the sum from n equals 2 to infinity of the natural log of n divided by n, must also diverge. Okay, and so that is the final solution to this example. We were able to compare our series to a smaller series that diverges, and so we can conclude that the original series also diverges. All right, let's look at one more example for this video. All right, so here's our last example. We want to use a direct comparison test to determine if the series converges or diverges, and this is the series we are looking at. We have the sum from n equals 0 to infinity of pi to the power of negative n squared. All right, and so what can we compare this series to in order to determine its convergence? Well, the first thing that we should do is rewrite this series a little bit. We can say that this is equal to the sum from n equals 0 to infinity of 1 divided by pi to the power of n squared, right? We can move that value to the denominator to make that exponent positive, and then what we can do is rewrite it again to be the sum from n equals 0 to infinity of 1 divided by pi to the power of n squared. Right, we can do that because 1 divided by pi to the power of n squared would be equal to 1 to the power of n squared divided by pi to the power of n squared, and 1 to the power of any finite value is just 1, and so this would just be equal to 1 divided by pi to the power of n squared, which is what we have right here. And so we can rewrite that to be this expression. Okay, and so now we have a series that looks like a geometric series, but it's not quite a geometric series because we have a value raised to a power of n squared, not just n, right? A geometric series has a common ratio raised to a power of n, where n is raised to the first power, not the second power. And so what we can do is maybe compare this series to a geometric series where the power is just n. All right, so we will compare this to the sum from n equals 0 to infinity of 1 divided by pi to the power of n. That is what we are comparing it to. I just want to make sure that that's clear. This is not equal to this. We are comparing them. And so this is a geometric series where the common ratio r is equal to 1 divided by pi, and 1 divided by pi is going to be less than 1. And so since the absolute value of the common ratio would be less than 1, we can say that this geometric series converges. All right, if that common ratio is greater than 1, then we would say it diverges. But in this case, it's less than 1, and so it converges instead. Okay, and so now we know that this geometric series converges, and so in order to conclude that this original series also converges, we need to show that this series is bigger, that the series we are comparing to the original is a larger series. And so let's compare the two series. We have 1 divided by pi to the power of n squared and 1 divided by pi to the power of n. And so what's going to happen to the value of these terms as n gets larger? Well, when n equals 1, both the powers of 1 divided by pi are just going to be 1, right? We have 1 squared, which is 1, and then just 1. And so when n equals 1, we have 1 divided by pi is equal to 1 divided by pi. But what about when n equals 2? Well, then we're going to have 1 divided by pi to the power of 2 squared, and that's just equal to 4. So we're raising it to a power of 4. And then our other term will be 1 divided by pi squared, right? We're just replacing n with 2. And so comparing these two terms, which one is bigger? Well, if you're multiplying 1 divided by pi by itself 4 times, that essentially is 1 divided by pi times pi times pi times pi, and 1 divided by pi squared would be just 1 divided by pi times pi. And so this denominator is larger than this denominator. And when you have a larger denominator, that value will be smaller than the other value, right? So 1 divided by pi to the 4th power will be smaller than 1 divided by pi squared. And so we can write that down. 1 divided by pi raised to the 4th will be less than 1 divided by pi squared, and that is going to continue to be true as the value of n increases, right? We're always squaring n for this term, and n is only raised to the 1st power for this term, and so this power will always be greater than this power, which makes this denominator greater than this denominator. And so 1 divided by pi to the power of n squared will always be smaller than 1 divided by pi to the power of n after n equals 1. So we can say that it's smaller when n is greater than or equal to 2. All right, and so what we have just shown is that our series that we are comparing to the original series is a bigger series. In the long term, for values of n greater than or equal to 2, this series will be larger. All right, and just a quick note, I did skip n equals 0. That wasn't on accident. If n is equal to 0, we're just raising 1 divided by pi to the power of 0, and so both terms are just 1, and so they're equal. We didn't really need to check that, but for values of n greater than or equal to 2, this series will be bigger than the original series. Okay, and so we have shown that a series that is bigger than the original converges, and so that original series must also converge. All right, and so our final conclusion is that since the larger series, the sum from n equals 0 to infinity of 1 divided by pi to the power of n converges, then the smaller series, the sum from n equals 0 to infinity of 1 divided by pi to the power of n squared must also converge. All right, and so that is the final solution to this example. We found a bigger series to compare to our original series that converges, and so the original series also converges. All right, and so with that, this was the last example for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.